Perth Linux Users Group, talking Linux and open source.
To be a local engineer for DDN storage. And oops, I sort of came along just to, I've been sort of looking through the meetup groups to find interesting people that I might like to meet up with basically and get to know sort of thing. So I can know some people over here in Perth. I've only been here since May. And yeah, I thought I'd do a presentation just to introduce myself and introduce DDN a little bit. But obviously, I don't want to do, I'm not a salesperson. I don't want to do a full sales spiel. So I'll try and talk to something that's a bit more interesting than just what we do. So just about myself, I've been working in IT for about 20 years now. I started sort of working with desktop publishing. I started with a Macintosh computer at home, and so always knew a bit about those, and they were very popular in the desktop publishing industries. That was where I started. Then I went to work for a couple of ISPs for a while and learned about networking. I worked for an open source consulting company in Melbourne called CyberSource, and I basically became the go-to person for Windows and Linux networking, and decided I didn't want to do that anymore because I didn't like doing the Windows side of things. And then went to work for RMIT University in the SET portfolio, or Science, Engineering and Technology. And it was there that one of the guys said to me, can you build us a HPC system? And I went, yeah, I guess so. And emailed a friend of mine from the Linux Users of Victoria, who I knew had been setting up HPC systems, and said, Chris, how do you build a HPC? And he went, well, start here. And I met it was for an engineering group, and they use a software called not OpenFOAM at that point, Fluent, which is a CFD solver. And so they asked me to get that running, and so I met a guy called Suda at VPAC, who was an engineer, and he told me how to get Fluent running. And about 8 or 9 months later, RMIT had made various promises, then reneged on them. So I said, Chris, how much do you pay anyway? And so I started working for VPAC at that point in time. And because I'd already been working with essentially the same stuff that they had been using internally themselves, I just slotted in fairly naturally to there. After 6 years at VPAC, basically I was setting up on average, so I was systems administrator for VPAC, and basically building clusters for engineering group. VPAC had a very strong engineering team. They worked with people like GM Holden, GKN Aerospace, Boeing, DSTO, various organizations in engineering and aerospace. And so I was there for a while, and then towards the end of my stint there, I got involved in a project at the Australian Synchrotron and Monash University, setting up a HPC solution that was provided by IBM, and this was going to be a hybrid Windows Linux cluster. So the nodes would run Linux, and then you could tell them to reboot into Windows for one of the applications that they were running. And what made that particularly fun was also that the storage involved was going to be IBM's Gpfs. So my first introduction to Gpfs was to try and get it working under Linux and Windows at the same time, and it was good fun. And because of that experience with Gpfs, later on IBM came to me and said, we need somebody to go to the Victorian Life Sciences group who have a Blue Gene queue, a couple of iDataplexes, and Gpfs underpinning everything. And they said, can you come and maintain their Gpfs cluster? The guy we've got there needs to move on and go do something else. So that was how I wound up at IBM. And technically, I don't think I actually ever worked for IBM. They paid my paychecks, but every day was spent at the VLSCI. And then, yeah, after about 18 months there, IBM, I may get killed for saying this, sort of, but IBM decided they were going to get out of HPC, more or less. They dropped their x86 lines, sent them off to Lenovo, and while they still do have the Power CPU and they're doing some stuff with that, unfortunately for me in Australia doing HPC stuff, they seem to be intent on just bringing out American engineers to do the HPC on Power solutions. So there was just nothing for me to do there. So DDN had been trying to recruit me for about a year because DDN do storage, and their storage is Gpfs and Lustre as an alternative, so 2 parallel file systems. So now I'm working for DDN doing Gpfs in Perth, and so that we've got the Pawsey Centre, if you've heard of that. This is the HPC Centre they set up to deal with the data off the SKA. So they have a small Gpfs installation there, and a Lustre installation, and a CXFS installation, just to keep things interesting. So that's where I'm working at the moment, and yeah, over the years I've messed with all of those and had to maintain them to various levels. So quickly about DDN, we basically were founded to build high-performance storage for HPC solutions. So we have the SFA product down the bottom here is sort of the building block. That's just pure block storage built to go fast. That's all it does, go fast. If you go and have a look at any other vendor's stuff and look at the features, you won't find any of those features on here. All it does is go fast and is reasonably fault tolerant, but you won't get any mirroring and all that sort of stuff that you get in other more intelligent block storage. But what we do for those extra features is layer on something like Gpfs, which can do all these sorts of replication that you want to do, data migration, full backup solutions. We use Gpfs for that. If you just want to go pure fast storage, you go with Lustre. Just purely fast. Occasionally goes bang, but mostly goes fast. And a lot of the HPC centers you can find around the world, they'll actually have a solution which is both Lustre and Gpfs. Lustre being scratch, really, really fast, doesn't matter if it goes away. And then they put all their data, important data, all the results and stuff like that on Gpfs where it gets backed up. They have multiple copies of it, and they can move it around to different areas reasonably well. There are very good tools in Gpfs for migrating data around in parallel. The other thing we have was down the bottom here, this is web object storage. This is a recent thing for us. Basically, it's a pure object store. So we don't have a file system underneath. It just writes objects to disk. And it's got a lot, this does have replication and stuff like that, so we set up multi-site replication, and we have hot heap mapping and stuff like that, so when data is being used more at one site than another site, gets replicated. So that's fairly intelligent, but again, it's just sitting on the SFA storage, and yeah, got a policy engine over the top of it. IME is not quite released yet. Burst buffers are a very popular topic for HPC at the moment. Basically, the idea is that if you want fast disk storage, you need a lot of spindles. But the more spindles you have, the more storage you have, which is kind of good, kind of bad when you go and sell somebody basically 9 petabytes of disk to get them a 1 terabyte per second file system, and all they needed was maybe a petabyte of scratch, if that, but you've got to sell them 9 to get the performance they want. So IME is basically just a cache that we build in front, and it actually takes the data fast. So these things are pure flash, write the data in fast to them, and then trickle out to smaller sets of disks out the back. And that's all that is. What does make this kind of interesting is to get the performance, the extreme levels of performance, is we've actually started hacking into the POSIX layer on, there's actually a shim that sits on the Linux, on the clients on this, and intercepts POSIX calls, because I think it takes 13 POSIX calls to open a file for writing or something like that. I'm not sure, certainly details exactly, but we've got it down to apparently 3 operations to open a file. So just reduction in the overhead needed to open up a file and write to it. Anyway, so yeah, that's essentially what we do. So we have, as I said, Lustre, if you haven't heard of this, is a parallel file system that was built by Sun. Sun gets bought by Oracle. All the engineers basically got to Oracle and went, nah. Left and formed a company called Wham Cloud. There is a thing called OpenSFS, which I think is a parallel file system steering group, and they're independent of this. Wham Cloud were a development group specifically for developing the engineering into Lustre. And DDN was a partner in that. Intel, Sun, I think, sorry, no, Sun wouldn't have been there, but yeah, various companies were sponsoring WAM Cloud to do the development of Lustre. And Intel bought WAM Cloud, and they have now these editions. You can still get the community edition. It's all free. You can do whatever you like with it, but they have their supported Foundation Cloud editions, and we just have a little version of our own that we still commit back to the community version. But as it says up there, they receive all the patches that anybody produces, but they integrate it on their own schedule. So they have certain things that they want to get prioritized. They put them in their own order. So we take the Intel-based Lustre, and we support standard Lustre or community edition Lustre if you want. But by preference, if you don't state a preference of your own, you'll get ours, and it's just the Intel-based Lustre with some patches to make our storage go a bit faster. Gpfs started as a research project. Tiger Shark FS. I recently joked, so Gridscale, or Gpfs was recently rebranded by IBM as Spectrum Scale. And somebody asked, what implication does this actually have? And I said, basically it means there's another layer of acronym commands on top of what's already there. If you go and have a look in the binary directory for Gpfs, you'll find commands that start with TS, which are Tiger Shark commands. There are also commands that are MM, which are multimedia file system commands. And now there is a Spectrum Scale command as well on top of all of that. So it's just wrappers on top of wrappers. IBM does like their backwards compatibility. Forever. So yeah, it started out as Tiger Shark FS, picked up some features from Vesta FS, which was a parallel file system that was hooked into the Multics mini computers. Finally released as Gpfs in 1998, so it's been around for a while. Lustre, I think, was only early 2000s. So it's not been there quite as long. And IBM, obviously, when they build anything, it's going to be built for an enterprise solution. So it ties into their TSM system for backups, and you can do HSM and stuff like that off it. And there's another name that I can't remember right now, but there is another product that they have that uses Gpfs in the back end, but it is basically a full life cycle solution for data. So just to give you a quick overview of sort of how these things work, the nice thing about both Lustre and Gpfs is how they scale. So these are our disk arrays. Basically, you've got the two controllers on top of disk trays. We can get up to 20 of those disk trays attached to the controllers. We usually set them up in lots of 10. One of the things about Gpfs and storage is if you want a nice multiplier for storage blocks sizes and stuff like that, if you take 8 disks in a RAID array and 2 parity disks, 8 times 128 gives you 1 meg block size. So we typically do 8+2 RAID on most of our systems. And yeah, just gives you a nice aligned I/O. So that's your fiber channel, or in our case, we actually use Infiniband. So we get 40 or 56 gigabits a second on our out of our controllers. I think we get about 8 ports per controller. And so nice SAN there, goes on forever, and you can just keep stacking these disks out. So if you need to expand your capacity or your disk performance, just keep adding them out sideways. If your network to your clients is slow, these are what we call in Gpfs or NSD servers. So, sorry, these are NSD disks or network shared disks. And these are the NSD servers, so they basically share those disks out to the network, and then you create a file system over the top of that. You've got distributed locking, distributed writes, and fault tolerance. So we build a cluster out of your NSD servers up here, and if one of those goes down, we lose a little bit of performance. bring up a new one. So if we want more network capability, we just add more NSD servers. We can handle more clients, handle more network I/O. Lustre is essentially the same. The only thing is they call these, they've got a couple of different names. There's metadata servers and object storage servers. So OSSs and MDSs for the servers. And then your disks are actually called MDT or OST, Object Storage Target or Metadata Target. One of the biggest differences between Lustre and Gpfs is that Gpfs allows you to mix and match your metadata pretty much any way you like it. So you can set some of your metadata on one set of disks. Sorry. Yeah, you can have metadata and object going to any of the NSD servers or any of the disks, and you can partition that any way you like it. With Lustre traditionally, and they're slowly changing this, you had to have one server initially. It was active, passive, an active metadata server that was unique in the cluster. So if that went away, all of your metadata went away. And there was an active passive situation, so you could bring up your passive one and bring the system back online. Gpfs, as long as there's a node up and the cluster is functional, you've got access to your metadata provided again. One of the things we do is map these drives, and usually you build a bit of a round robin. So at the moment I've got 8 NSDs, and I've got 8 NSD servers, NSD 01 to 08. I've got a whole bunch of disks, and I map one disk to 4 NSD servers. So basically, I've got 1 in 4. So 4 nodes would have to go down before I lose access to that disk. And you can do that with metadata or data. Doesn't matter. So that's essentially how that comes together. And the clients do have to run a client on the node to participate in that cluster. And because it's distributed locking, you can, each node can have a lock on a file, and so the nodes have to be able to talk to each other to get access to that file. And we have actually had situations where people are like, no, we don't want the nodes to talk to each other. It's like, yeah, you're not going to get your locking then. Gpfs also supports the idea of remote clusters. So we can actually have, well, in the case of VLSCI, we have a storage cluster in the middle, and that owns all the disks, and it owns all the file systems. And then each cluster, so there was Mary, Avoca, and Baku, Victorian rivers, apparently. And Avoca was the blue gene, and Baku and Mary were both iDataplex clusters. And each one of those would be a separate Gpfs cluster, and it would remote mount the file systems off the central cluster. And it meant that we could do a lot of work on individual systems without interfering with anything else. And one of the things that I was quite happily able to do is basically do upgrades of Gpfs, rolling upgrades. You upgrade a node, restart it, upgrade a node, restart, upgrade a node, restart, nobody notices. Everything just keeps humming along. That's actually my favorite feature of Gpfs, is it's a very fault-tolerant, and Lustre is similar. Very fault-tolerant system. You can reboot your nodes individually, and you lose a little bit of performance during that period, but usually we're not maxed out. Usually we've got a little bit of overcapacity. So, main topic, what is HPC? Simulation. Bulk of what goes on in HPC is around simulation. Weather forecasting is an obvious one. Geological mapping, possibly not so obvious, but there's a lot of people who suddenly realize that this is a really good idea. We actually built a bridge, sorry, not a bridge, but a pier down in Victoria. Somebody just decided they needed an extra pier off into the coast to tie up some boats to. Didn't think to do anything, study the water around it. So what's happened is the water coming down the coast has run into the pier and started circling, and basically eating away at the coastline where the pier goes into. So all of a sudden the coastline is disappearing around where the end of the pier is. So if you can do geological simulation before that sort of stuff, and measure that sort of, get some ideas of that sort of stuff, that's great. One of the other ones we had was rip tides and stuff like that for surf coasts, marking them in and doing some processing to try and figure out what they were going to be like for the day, and then we could also assign people out and make sure there were lifesavers covering those areas. Engineering simulation, this is a fun one. At the moment, if you want to build a car, you've got to crash about 100 of them to make sure they're safe. That's a fairly big expense. So if we can simulate more of those crashes in a computer, then we can cut down on those costs and make it manufacturing cars. And you don't have to necessarily crash the car in 15 different countries. But also, we will probably still crash them, but instead of crashing 100, we might just crash 4 just to make sure that what we're seeing in the simulations is still matching up. One of my favorite stories was a company that was doing defense, and these guys built an armored vehicle. Now, apparently in Australia, we can't test those to any standards. They have to go to either the UK or to the US to be tested to confirm that they will actually not blow up or protect the people. So they shipped one of these things off to the UK. It cost them $2 million to ship it there. In the UK, they blew it up. And after successfully blown up the transport, they went back and realized that they hadn't turned the sensors on. So they didn't have any data. So Q shipping another one for another $2 million to the UK to blow it up again. Let's not do that. And one of the guys, the engineering team at VPAC is actually working on a zero. I don't know if they'll ever get to absolute zero. Well, eventually we will trust these things. Eventually computers will just be, yeah, you do it all on a computer and it's never going to miss. But yeah, they are aiming for zero crash. They want it all done in simulation. Biological process simulation. This is what VLSCI was essentially doing. This is about protein folding, docking drugs and stuff like that. So we want to emulate the processes that go on in the human body. So when we build a drug, we can see that drug binding to the virus or whatever. And again, the more we simulate, the less we have to test on animals. Analysis, image processing, signal processing. So this is what the Australian synchrotron was doing. They had CT scanning. So they would take 15,000 slices or images of an object. And they started out small. And of course, as soon as you tell a scientist you can do something small, he will say, great, now we want to go bigger. But I think they were 15,110 meg images, and they want to apply a filter to those images. So what we did was built a system so that they could take the data straight onto the Gpfs file system and then run it through a cluster that would reconstruct those images or apply that filter. And one of the reasons why they wanted to do it fast was because some of these things, they're biological, and the light coming off the Australian synchrotron is basically destroying the sample as it's taking photos of it. So they want to get near to real-time reconstruction of this image data so they can make sure that they've got the data that they need to get. And if they haven't, go back and try again. Signal processing. I've actually forgotten what example I had for that. But yeah. Oh well, I suppose this is basically PAWSY. This is what they're doing. They're going to take signals off the SKA and analyze them for different features of the. Sorry, lost slightly. So the SKA, square kilometre array, basically it's looking at space. So we're looking for signals coming off pulsars, quasars, anything you want. The fun thing about the SKA is every time I turn around, they keep on bringing up a bigger number of how much data they want to get through every year. I think we're at 5 zettabytes a year or something ridiculous. And most of it is going to be thrown away. But they have to filter it first and make sure that they're not throwing away the stuff that they want to keep. So there will be some processing there, and then what they want to keep, they'll write to disk. But as far as I can tell, what they've actually said is they are going to take a picture of the entire sky every time they take a picture. And then they only want this bit. So we'll throw away all the rest. it means you get, instead of just this bit, you get everything around it as well. And so you can keep more than you necessarily would on a traditional telescope, and with more detail. Statistical analysis, I think that was about, they do some statistical analysis in banks and stuff like that these days. They will actually send off, not a big HPC job, but just one of the things that I was going to introduce a little bit earlier is the concept of high-throughput computing, which is kind of like high-performance computing, but it's just about getting a lot of small jobs through. So in these bank situations and stuff like that, they just have a little package of work that they want to get done in a very short space of time because they want to return to the customer that they're dealing with on the spot. So they have this cluster, and all it does is take these 5-second jobs through at a constant rate. Last, creation. And this is something that's probably reasonably obvious, but yeah, video post-production and animation and rendering and stuff like that. So you take the Western Weta Digital, very popular in New Zealand. A lot of the animation for all the orcs and stuff like that came out of Weta Digital, running off a cluster. Video production, similar thing. You may not be animating the scene, but you might decide you want to put a filter on the scene, make it darker, make it lighter. You can use a HPC to just do that in real time in the background. These days, a lot of that can be done on graphics cards, but what they often do is they actually bring it down a resolution, do it on the graphics card, and then try and apply that later to the full resolution video because they can't necessarily process that in real time. So different types of workloads on a HPC solution, and this is a little bit of going what I was going on about just before with the high throughput computing. We have tightly coupled problems. So when you've got an engineering simulation, you've got a model that you want to try and simulate the effects on or behaviors of, that you can't easily break up because every time you do these simulations over a time cycle, and every time step you need to synchronize the data across all the nodes in the cluster. So you want to do that at with a high-speed interconnect because otherwise you've got your nodes sitting there waiting for the data to come through. So if you want to keep your throughput up, you do that. Loosely coupled problems can be set over disparate systems. So like that bank simulation, those little packets are not necessarily interconnected on anything. They take 5 seconds. So you can just throw them on any node that happens to be free at the time. And you don't have to worry about the data being expressed. So you can do things like cloud bursting, where cloud nodes, they have a good amount of CPU, but they don't necessarily have good connectivity between each node. Doesn't matter in this instance. You just throw it out there, wait for every little packet to be done, bring it back. It's all good. Large data set sorts that can't be parallelized. This one I don't know too much of, but one of the clusters that I helped work on for a while was out at forget it, but these guys were doing genome reconstruction, and from what I can tell, genome reconstruction, each stage of the genome that they're trying to assemble actually relies on the previous stage to determine the following stage. So basically, they've got these great big genome databases that they need to assemble in order, and they can't parallelize these things. So what they do is they throw all of the data into memory. They get by 1 terabyte and 2 terabyte nodes, throw all the data into memory, and then have a single thread just churning through, attempting to do matches on these sequences. So, and of course, the only nodes that can give you a terabyte of memory, or 2 terabytes of memory, have usually 16 core CPUs or 4 sockets or something like that. So you've got 16 idle CPUs and 1 thread going flat chat trying to sort through all this data set. It's a bit mental. And with that, you get different types of clusters. And these clusters are better at different tasks, basically. I don't see too many of these. The single OS image NUMA clusters. So the SGI Altics was fairly typical of this. Basically, when you logged into an SGI Altics, these things were made up of bricks, and each brick was essentially an individual computer, but they had a very high-speed NUMA link connecting the CPUs. And you booted one of them, and you booted into Linux, and all of the others just became part of that one OS image. So you logged into one of them, and you saw all of the CPUs, all of the RAM, and it just looks like a single Linux box with really, really, really big numbers of CPUs and memory. Now this is good in some instances because you don't have to reprogram your code for things like MPI, which is a message passing interface. Sorry, which is a message passing interface. So that reduces some of that ability, but it also, I don't think, scales very easily, and I think that NumaLink connectivity is fairly expensive because it's probably lower latency than InfiniBand, higher bandwidth, and also I think this is one of those things where it's getting better, but once upon a time, if you lost a NUMA node in your cluster, the whole lot went. Because you've just lost all this information that the cluster was using. It's gone. So multiple OS image MPI clusters was the next one. Is any typical BOF cluster that we build these days. So every node in the cluster runs its own Linux instance, and we have InfiniBand to provide a high-speed interconnect, high-speed, low latency. Low latency being the more important part. And yeah, each process communicates with other processes on the other nodes via the message passing interface. This does mean, yeah, you have to know to write with MPI. You have to do sorts of some fairly high-level programming tricks to try and make sure that you have to know to divide your model up appropriately, spread it out over the nodes. You don't want to spread, basically, you need to make sure that the data you're sending around is not going to be heavily used in one spot, and so you're going to generate a lot of traffic over the network. So you've got to have a very good understanding of your model before you break it up. But it works. A lot of stuff is done that way these days. The IBM BlueGene vector coprocessor. So this thing actually has, with a BlueGene, there's what they call launch nodes, which are just power-based nodes. And your job runs there, and then each node on the BlueGene runs a little microkernel that has been open source, I believe, and actually can just run a single thread from the application. So it is really just basically a vector coprocessor on those launch nodes. And so yeah, that works really well for some things, but you have to rewrite a lot of your code. But we seem to be doing a lot of that these days anyway, even with the using GPU stuff. You have to rewrite your good sections of your code to try and push that data out onto the GPU. It's a very similar thing. I think I essentially covered a lot of that. One of the things I will note, yeah, netlock and HWlock, things that have come up recently. Well, I suppose 2 or 3 years now. And basically these are about trying to get the MPI stack to understand the topology or the how close nodes are and how close CPUs are and stuff like that, so that they can actually organize the data better when they go to run a job. Challenges, modeling, yeah, so basically, yeah, understanding the models, understanding how to break them up so that we can not try and spread the data out too much and keep the stuff that is going to be interacting a lot together. Software, this one's almost continuously a problem. People tend to invent new languages and then add parallelism to them, and then nobody goes and adopts them. So then they try to bring those features back into other languages, but then the people who are writing the code don't understand what they need to do to write code. So that last line there, need more cross-discipline developers. We really need people who understand biological science and programming, physics and programming. One of my friends rewrote some physics code that tracked, I think it was molecules as an atom was being exploded. And particles, not molecules. And yeah, this thing took, to track 1 million or so particles, it took a week or so to run this code. And he sat down and went through, and I don't know anything about coding. I should actually say that. I know very, very little about coding. I try to avoid it. I do a little bit of scripting and stuff like that. But even I know about linked lists and various other features in languages. And he said that's all he did was sit down and go through the code and use some very simple C structures and stuff like that that just about anybody who had been writing C for more than about a year would know about. And he went from a week to about 5 seconds. So it's really good to know both worlds. If you can get that, because a lot of the people who are writing the code are unfortunately scientists, and their primary interest is their science, their physics, their chemistry. And that's wonderful. That's what they should do. They shouldn't have to worry about it. But we need to know more about programming, and we need to know what they know about so that we can talk to them about the problems that they're having. Hardware reliability, more hardware, more failures. The biggest supercomputer cluster in the world at the moment, well, sorry, not the Chinese one, but one of the bigger ones in the US has a hardware failure on average about 1 or 2 a day. And that makes it really hard to run a really big job if your hardware is going to fail on that sort of regularity. More pieces, more failures. More hardware, more power and cooling. The biggest challenges facing Exascale. We could build an Exascale size, so at the moment we're talking about petaflops, petascale computers. I think the biggest ones are around the order of 2 to 3 petaflops. They're aiming to come out with 10 petaflop systems fairly soon. Exascale is the next one after that. They're suggesting that basically you could dedicate an entire nuclear power plant just to running the interconnect, not the nodes. So just the networking, one whole nuclear power plant. So we need to be able to get some of that stuff down. Some of that is coming along. We're finally getting fiber optic coming along more reliably. It's just been expensive. The price of that needs to come down. And of course, yeah, Intel are having lots and lots of fun with their 14 nanometer process. This will be, everybody cross their fingers when they go to 10 nanometers. This could take a while. But yeah, you're basically putting in more and more power and cooling, almost more than the system is these days. The cost of the system is cheap. It's the power and the cooling. Changing landscape. You can get 64 or 128 cores, 2 terabytes of RAM in a single node these days. What do you need a big cluster for in a lot of circumstances? One of the things we did with engineering clusters and stuff like that is they basically came up with a thing where they're trying to simulate a car crash, and it might take them normally a week to do that. And they say, okay, we need to get this down to something a bit more manageable. We need to be able to turn this around in a day. So you build a system, you say, okay, we can do that. They do that usually on their desktop or a couple of desktops. So if we can get that down to a day in a 128 core system with 2 terabytes of RAM, and then you just build building blocks, and that's where you don't need the interconnects for some of these. So we just build building blocks of 128 core nodes, 2 terabytes of memory. It's all good for them. Cloud services, again, we sort of covered the pros and cons of those. They're great for cheapness. University can spin them up. You pay for them as you use them, and then you put them away. But yeah, you don't necessarily get the interconnects, so they're really only good for certain types of problems. You can get the interconnects on some of them. I think IBM's software and Amazon will both sell you systems that have very good interconnects on them, but you wind up paying almost as much as you would have if you bought the bare metal outright. So it's pros and cons. Sharing of data is a good fun one. Nobody wants to move 2 petabytes of data anywhere. It's a really bad idea. I don't know if anybody has done much or heard much of the European grid and stuff like that. So there is a thing called the grid, and there's a US one and there's a European one. European one, funnily enough, centers around CERN and the Large Hadron Collider. And this thing generates 14 petabytes of data a year or whatever. And the grid basically means that a scientist anywhere in the world can say that they want to run with data from the LHC and submit a job, and it uses SSL to wrap the job up. So it wraps it up in an SSL certificate, and that's what your authentication is. And so clusters around the world have a whole series of accounts created that will accept those SSL certificates that are generated and run the job. So there's several rings. I think ring 0 is CERN itself. Ring 1, you need to have 10 gigabits to CERN and about 2 petabytes as local storage. And then ring 2 is pretty much everybody else, which is just all these little small clusters around the world. But when you go and make those requests, the requests were not necessarily aware of each other. And so you'd have these situations where two scientists working on the same local cluster might request the same amount of same data, and so 2 copies of 2 petabytes of data would come down. That's not good. So you've got to, one of the things that I'm looking forward to is NBN and stuff like that taking off and getting faster and faster internet. The other option that some of the cloud providers I was talking about is actually having data just always in the cloud. They will actually offer cheap storage to researchers and just leave the storage in the cloud, and you can pull it down anywhere. Let them deal with the bandwidth issues. Let them deal with multiple copies of it. Docker containers. One of the big fun challenges of HPC is software stacks, because everybody wants their own software stack. Everybody wants the newest version of GCC, and then if you install the newer version, you wind up with everybody else's application breaking. We use a thing called environment modules, which just set up an environment variable. So you can do module load GCC 4.10, and it will load up and set all the environment parameters to use GCC 4.10. But some people are starting to look at Docker containers for doing that sort of thing as well, because you can just wrap up your application in a Docker container, submit it to the cluster, and when it's done, you'll still have your Docker container sitting around. And one of the important things for some science and research data is being able to replicate your experiments. And if you're going to replicate your experiments, you need to have the exact conditions that you had, more or less, as when you generated the data in the first case. And so if you can wrap it up in a Docker container and keep that Docker container as your application space, then you will have the same version of the libraries, the same version of the application, and you can submit it again and hopefully get the same results. Patching Mesos. So that's a scheduling system that can do resource control or whole data center resource control. I haven't spent too much time on this, but a lot of people are saying, oh, why aren't you using Mesos for your scheduler? And it's like, because, you know, it's another thing. Quantum computing, D-Wave is taking off. Intel have apparently just announced a big investment into quantum computing, so that should be very interesting. D-Wave seems to have survived all challenges so far to whether or not they're actually running a quantum computer. So it looks like we might actually see some interesting stuff coming out of quantum computing. Cheaper custom manufacturing. I know you guys probably all know about the Raspberry Pi. Did you also hear about the Parallella board? Yes? No. It had an FPGA in it, but this was a company that basically went out to build a reasonably simple RISC-based chip that had a lot of cores. So you could buy for $100 a 16-core chip that ran on a 5-watt board. So 5 watts, 16 CPUs. I think it was around 2 gigaflops per core. So on a single 5-watt board, you got 32 gigaflops, which is not bad. And they also had a 64-core version for about $200. Still ran in 5 watts. Dirt cheap to manufacture this sort of stuff. They also had a 4 10 gig interfaces on it, a north, south, east, and west. And they actually, on their boards, they've got connectors to allow you to basically Beowulf cluster the boards, and they will do 10 gig over 2 ports, one on each side. And yeah, the FPGA was how they communicated with it. So it had a dual-core ARM to boot, and an FPGA to talk to the 16 or 64-core chip. And dirt cheap. Manufacture them easily these days. Anybody who knows how to do it can go and do it. It's still relatively cheap. I think they raised a couple of $100,000. This was actually a Kickstarter project, and I think they raised a couple of $100,000 to do this, and they ran over, but it's still getting cheaper all the time. And I think that is about all I had. So if you want to ask any questions, feel free. Get your... Oh. All right. I got the battery.
Question to see how does this relate with high availability system and mirroring? You know, like you use a high availability system and mirroring, for example, for trading flow. So if anything happens within a couple of seconds, you just basculate to another source. You know, you actually share the data in a way between various nodes, and
Yep.
It enables high availability. Within a couple of seconds, if a system collapses on one of the nodes, actually it basculates to the other. And it's used for mainly also in application or terrorists and place to protect banks. And so
Yep.
mirroring is really having a heap amount of data that's actually shared between various centers.
Yeah, and that was one of the big things about Hadoop, more than anything else. So Hadoop was a scheduler system that basically made sure it had 3 copies of data, and yeah, you would submit a job, and the job would find one of the nodes that had the data you wanted to work on it. We don't generally do too much of that because yeah, it is an issue to try and mirror the data around when you've got petabytes of it or terabytes of it. Some of the systems, the Pawsey system actually is running at the moment in a high redundant state. So we've got 4 of our arrays there, and Gpfs we've got each one of them is a failure group, and we can actually say we want 2 copies on independent failure groups. And so we're doing that at this point in time, but we'll probably remove that eventually because it does have fairly significant performance issues. I haven't personally, no.
There's a lot of money there.
Yes. But yeah, they tend to be very particular. We tried getting into a couple of banks, but they were, well, I never tried with IBM. IBM would probably have a lot better chance than I would. When I was at VPAC, VPAC was a small research institute, so they didn't really take us too seriously. But yeah. Yes.
Thanks.
That's right. Oh, just quickly, for interest, if somebody wants to have a look at it, this is a node card from a IBM Blue Gene P, and this is a quad CPU, 4 gig of RAM card, and they had this. This is essentially a computer. All the I/O was handled off board, and so you'd slot this into a big tray that had, I think, around 32 of these in a tray. And so at a Blue Gene P, I think we got about 4,000 cores per rack. The Blue Gene Q, 16 cores, or 18 cores, 16 usable, 1 spare, and 1 boot CPU, 16 gig of RAM, and in 4 racks you get 65,536 CPUs. But yeah, one of the things they had to do when they went from the P to the Q was go from air cooling, which is what the big heatsink is for, to water cooling, because there was just no way they could get the airflow through well enough, because these things were seriously, you wind up with two cards. Basically, your other heatsink sits there. So you got two cards sitting like that, and they just couldn't get the airflow through. So they went to water cooling, which made, of course, changing out a node board somewhat challenging because you had to drain the water out of them. But if you want to have a squiz at that was a going away present from the VLSCI when I left. Here, have our Blue Gene P. Yep.
Question about Infiniband versus Ethernet.
Yep.
Are the systems that you're using almost exclusively Infiniband? That's what it sounded like. Or is RDMA over Ethernet, is it becoming a thing? Or
It's becoming a thing. Some places are doing it. Some places they're more comfortable with Ethernet because it's something they already know and they already have. But primarily, if it is, and again, it depends on the problems they're trying to solve. If they think that their workload is going to be, and so this is where it becomes a little bit fun. The Blue Gene Q, you buy one or you buy a Cray for the interconnect. That's why you buy it, for low latency, high speed interconnect. So it's a bit sad when you discover that 98% of the jobs running on there are single node. And this is where we get into the politics and stuff like that, because you get these situations where, I was going to disclaim that at the start, a lot of the stuff that goes on in HPC at the moment is sort of US-centric and doesn't really relate to the rest of the world because the rest of the world doesn't scale quite as big as they do. The first time I attended a conference on high-performance computing in the US in 2008, they were one of the guys was talking about how to break up their clusters, how to break up their big cluster into 512 node chunks. And the biggest cluster I've seen at that point in time is about 200 nodes, and I think Australia's biggest was about 400. And he's like, yeah, no, I've got a whole series of 512 node chunks. And they just run into all sorts of troubles that we just don't get to as yet because we're not scaling that big. So coming back to your question, yeah, we have some fun with various nodes because, yeah, we went from this situation where when we started building BOF clusters, 2 CPUs, small number of RAM, if you wanted to scale, you needed InfiniBand to get onto more nodes and to get onto more memory. These days, with the 2 terabytes of memory in a node and 128 core CPUs, you don't have to scale quite so big to get the amount of performance you need. So yeah, in those situations, Ethernet is just used maybe for the I/O bandwidth, getting your files off disks and stuff like that, not so much actual compute. Does that make sense? Cool.
I was just wondering if you could talk a bit more about the work you did at the Pawsey Centre, as in, did you provide all of the computers for that, or was it just a chunk of it, or what?
No, so there's a little bit of everybody in there at the moment. So Cray are in there for the compute, and they sell a solution at the moment called Synexion for their storage, and that runs Lustre. And then SGI are in there with CXFS for a HSM solution that moves data off to tape. And then we're in there for RDSI, which is a national infrastructure for data storage. And so they just basically use us for storage for data that they will share with other universities and stuff like that at the moment.
The system will be storing the data that comes down from the SCAR from Murchison?
Eventually, maybe. Some of it.
So I don't know a lot about file systems, but how does Lustre compare to, say, like ZFS? Does it have things like deduplication, that sort of stuff?
No. No. Lustre is purely about performance.
Okay.
Sorry, slight correction on that. Lustre originally was built on top of XT3. So what would happen is you build your block storage. Sorry, you build your storage and put format your files. Format your storage on XT3, and then you would spread your writes and your files over XT3 blocks, and then you would use your metadata server to keep track of where that was. They've actually started building it now with ZFS as a backend, as an optional backend. But I don't know how much of the features of ZFS they're actually using.
but it is actually there, and I wouldn't be surprised if they can do some of that. But because you're not, I don't know how well it will work, because you're not storing all of your data on a single node. So where do you get your dedupe and stuff like that from? So I was actually kind of puzzled when they went to ZFS. Most people were sort of thinking they'd go with XFS possibly, and then of course eventually they are also aiming to go to BTRFS as well.
And would most of the data that goes through those computers, would that be like on Scratch? Because it's just, you know, you do a job and then you're done and you get rid of that, or is there much that's stored there permanently? Yeah, no,
Scratch usually should be basically just temporary stuff. One of the systems that I built in the early days, we built a large amount of disk on a Scratch file system because the application would write a 40 gig temporary file on exit. And so you needed to basically write that out quickly and then get rid of it. And some of them just use it as working space, so you can create files. Sometimes you stage data in and out, and it's annoying. Because you don't want to necessarily move your data sets out onto Scratch, but Scratch is often your best performing file system, so why would you not put it out onto Scratch? And this is where you get into user education and user fun. And this is where, again, it depends on how you want to set your file systems up, because certainly with Gpfs supports pooled storage. And so you can have a pool of storage that is Flash or SSD, a pool of storage that is SAS, and a pool of storage that is SATA. And it will actually intelligently move according to policies you build, move the data back and forth between those as you need. So what you should have really is everything in a single file system. Have all your hot data write to Flash, and then eventually migrate it off to your slower storage. But yeah, all of it requires a lot of complex setting up, and not a lot of people do it.
Howdy. Just going back to your diagram you had earlier about the I/O. Can you just give us a bit of a description of what's happening on your red and green links? What sort of transactions are happening between the servers and the disk, and then the servers and the clients?
Okay, so basically it is really just one is pure block transport. So iSCSI or so in our case, for the fastest data we can, fastest networks we can get, which are Infiniband, get the best throughput. So we use Infiniband, and there's a thing called SRP, which SCSI Remote Direct Protocol or something like that, maybe. And so yeah, we fire up SRP to present, but we can also do fiber channel if we want.
So your NSD servers are essentially, they have a block device attached.
Yep.
That's right. So what's the red traffic? That's your Gpfs or your Lustre?
That is your Lustre or Gpfs at your client nodes, yeah.
Right. Okay.
Yeah. Yeah. You don't have to separate them out that much, but it just makes it hopefully a little bit clearer as to what we do. And I mean, what we've got, we've actually got models of these that we call our E models. So SFA 12K X KA, SFA 12K, 12KX, and 12KXE. The E models are embedded versions, and we actually have instead of having the external NSDs, we have them embedded in the controllers. Saves a little bit of cost and a little bit of mucking around, because you don't have to have the external NSDs, but you do pay for it in performance.
So does that mean you're not mapping one disk to one LUN on your?
Correct. You would get Gpfs straight out of the nodes. Yeah. And of course, yeah, you lose. I mean, we get 4. So we usually run 2 VMs. These things run Debian, by the way, and we have a boot. A special boot environment that does all the disk controller, but they actually run Debian, and we run KVM for our virtual machines. And so we can, in the virtual machines, we usually run CentOS, install Gpfs on there, and so it's 2 VMs per controller. And of course, we're limited to whatever memory we have in the nodes, and whatever CPU. But I think the virtualization doesn't. We have our own driver for accessing the NSDs directly at that point, or accessing our storage. So normally, SRP presents them as block devices to the host operating system, and then we use something like multipath over the top of that to get fault tolerance, so we can do multipathing. And yeah, something about the virtualization just doesn't seem to give us this. We pretty much halve our performance.
Right, so using
But
like a Verdeo style access to your whatever your underlying store is.
And for people, it really depends on what they're doing. There's a couple of RDSI hosts who are happy with that because they're not really so interested in the storage. Putting on my sales hat briefly, this is less than half the cost of an EMC Isilon, and we usually do all right against NetApp, but I think once we get to about 5 trays, we are cheaper per tray to expand than someone like NetApp. And not only that, but our performance is just way beyond what they're trying to replace 3 of our systems at the moment with 18 of theirs. They just do not get the same amount of performance that we get through ours. Give you an idea, you'd have to see the back of these, but basically, in a lot of some of the systems I've done, one of them was a Dell system. You get loops for your connection, so you've got an iSCSI bus that runs sort of in loops down. We have 2 channels per controller all the way through for every tray. So there's 8 cards, I think, in each one of these. And there's, I think, 2, and that's where we get all of our performance. The only thing that I think comes close to sort of us in performance is the IBM XIV machines, and they run full bandwidth to every disk as well. No problem.
Well, thank you very much for coming along. That was
You're
really
welcome.
interesting. Thank you. So please, thank you, Matt. So we do have